Hey everyone, in this video we're going to work through another application of antiderivatives, if I can remember what I'm doing here. This is one that in a face-to-face class I would have people work on in groups, so I especially, even more than usual, recommend that you pause and try and work through some of this on your own and then check back in. Okay, so we have a train that accelerates and decelerates at the same rate, 4 feet per second. We know its maximum cruising speed is 90 miles per hour. And our first question is, what is the maximum distance the train can travel if it accelerates from rest until it reaches its cruising speed and then stays at that speed for 15 minutes? I see my own typo, stop. We are not trying to stop at the end of the 15 minutes. Okay, so I'm spotting one thing right away. I have this 90 miles per hour that I would like to convert to feet per second. So if this is 90 miles in 1 hour, we're going to say 1 hour is the same as 3,600 seconds. And 1 mile is the same as 5,280 feet. And I preemptively crunch these numbers, and I got 132 feet per second. Okay, so now we're going to try our typical trick of starting with acceleration. We're interested in the speeding up part, not the slowing down part, so we'll say we have an acceleration of positive 4 feet per second squared, which means our velocity function will be 4t plus t sub 0, t sub 0, v sub 0, feet per second. In this problem, we're starting from rest, so our initial velocity is going to be 0, which means that our position function is going to be 2t squared plus s naught. And same thing here, kind of same thing. We're starting off at a stop and we want to know how far we get in 15 minutes. 15 minutes plus the speeding up time. So our initial position is going to be 0. We initially haven't traveled anywhere. We want to see what happens after that. Oh, yawning again. Okay, so we want to figure out how long it takes for this train to get up to speed. So one mistake that I'll see people make here is they'll just take the 15 minutes and they'll plug it into the s of t function. And that's not going to be right. It's not accelerating for 15 minutes. It only accelerates until it hits its 90 mile per hour speed. So we want to know when this is true. And what do we get there? 633 seconds. Okay, so it takes this train 33 seconds to full speed. And during the 33 seconds that it's speeding up, it will travel 2 times 33 squared feet. Which is going to end up giving me 2,178 feet. Okay, so this is information only about when the train is accelerating. After we've traveled the 2,178 feet, we have to proceed to spend 15 minutes traveling at 132 feet per second. So this is the at max speed part. We'll be going we'll just say it this way, the distance will be just a nice simple distance equals rate times time. So our rate is 132 feet per second. And then we want to be a little careful here. This is 15 minutes. So we need to multiply that by 60. And we end up with 132 times 15 times 60. 118,800 feet, which we could certainly convert back to miles at this point. So we could divide by 5,280 and say 22.5 miles. Okay, so there's part A. The rest of the parts are just variations on this. So we'll keep working through, but again, if you got stuck on this one and came back and watched, nobody yawns, make sure that you pause again and try and work through the rest of these on your own. Okay, so now we want to start from rest, and then we need to stop again within our 15 minutes. And we need to figure out the maximum possible distance it can travel. Okay, so we don't get to just keep going for the entire 15 minutes at max speed. So we've actually done a fair amount of this work. We know that to speed up takes 33 seconds, and you travel 2,178 feet. And slowing down should actually be really similar. We're reversing the process, but if it took us 33 seconds to get up to speed with an acceleration of 4 feet per second, then slowing down should also take 33 seconds. And we should also cover 2,178 feet during that time. So if it helps at all, my visual on this is we speed up, we have constant acceleration, and then we maintain that velocity, and then we slow down, and we have some definite symmetry going on these two parts. Okay, so speed up, slowing down, and then at full speed. Okay, so we have a grand total of 15 minutes. It's too early for me to multiply. Which is 900 seconds. I guess it wasn't really too early. That was really lazy of me. Okay. That does not mean that we will spend 900 seconds going 132 feet per second. We have to subtract out the 66 seconds that we spend speeding up and slowing down. So we're really only going to spend 834 seconds at full speed. Which means that our distance at full speed is 132 feet per second times 834 seconds. Which is, oh, hold on, I'm doing it for the whole thing. So let's do 834 times 132 is 110,088 feet. And then if we add this all together, 2178, 2178. We we get 114,444 feet total. And if we compare, let's see here, what did we get before? We got 118,800 feet, so that seems reasonable to me. We're not going to make it quite as far because now the speeding up has to be included in the 15 minutes, as does slowing down, but it's not drastically less. Okay, and same with that one. We could convert that to 114,444 over 5,280, 21.675 miles. All right, part C. Now we want to know the minimum time to travel between two stations that are 45 miles apart, assuming that we're stopping on both ends. So now we know our total distance is 45 miles. So let's see, we need to do the same sort of thing as before. We need to speed up, which takes 33 seconds and covers 2,178 feet. I'm going to trust myself not to put digits. 2,000, yep. And we need to slow down, which takes 33 seconds and covers 2,178 feet. So if we take our 45 miles, we multiply by 5,280 feet. We get 237,600 feet that we need to travel total. We know we need to subtract off the 2,178 for speeding up, the 2,178 for slowing down. And I get 33,244, not point, feet. Okay, so we know that we spend 66 seconds total to speed up and slow down. We want to know our minimum possible time. So what I would want to assume is what I've already started assuming, that we're speeding up all the way to full speed and that we get to maintain full speed for the entire time until we have to start slowing back down to stop at the second station. So what I really want to know is if I take the 233,244 feet and I divide it by my 132 feet per second, my maximum speed. 232.44 divided by 132. How? Whoop, not my knee. That thing's popping up on my screen. How long did it take me to travel that distance at max speed? And the answer is 1,767 seconds. So if we add back in our 66 seconds, 1833 seconds. And we could even divide that by 60 and say that's 30.55 minutes. Or roughly half an hour. Okay, one more part. If we know that the trip from one station to the next takes 37.5